Hello everyone, and welcome back to the series on intermediate statistics. Today we're going to continue our exploration of estimation theory and discuss a very useful and basic method that can be used to generate estimates for any moment that you want, provided that it even exists. And the only thing you have to do is solve an algebra problem to find those estimates. So let's just recall a couple things that you should know up to this point. So recall that the jth moment of x, commonly abbreviated by e of x to the power of j, in the discrete case is the sum across all values of x in the support of your PMF, p, of x of j times its PMF. And for the continuous case, we integrate over the support, say from minus infinity to infinity, of xj times the probability density function fx of x. Since we're only going to be working with finite samples most of the time, we're going to be primarily focused on the discrete definition of the jth moment of x. Right? So let's suppose we approximate, if we're only considering the discrete case, the probability mass function to be approximated by fx of x divided by m. So in case you don't remember this notation, this is the frequency of element x in our sample of size m. So technically speaking, we can say sample s of size m. Sample s, where this cardinality of s is equal to n, finite. That's that little n on the bottom. A couple other things that you might remember about this representation. The frequency divided by n sometimes is called the relative frequency. Relative frequency, and has the property that the sum of the frequency divided by m is equal to 1. And also the frequency divided by n is always between 0 and 1, similar to the properties of a probability mass function, px of x, which makes it a suitable candidate for its approximation. So now what we want to do is we want to approximate the jth moment of x with something that resembles this particular structure. So using this candidate for approximations of px, what we can do is just simply say that the expected value of xj, or the jth moment approximation, will be approximated by the sum across all values of x of xj times the frequency of x divided by m, for which we can equivalently write as 1 over n times the sum across all values of x of xj times the frequency of x. And keep in mind what the sum ranges up to. The sum is over all unique x inside of your sample. So technically speaking, we can range that sum from k is equal to 1 to n if we treat all of them as distinct, or we even ignore the repetition of elements if they happen to have a frequency bigger than 1. Right? So let's suppose that our sample can be written in the following way. x1, x2, all the way down to xm. Then that means the jth moment can be approximated by 1 over m times the sum from k is equal to 1 to m of xk to the power of j. Here, it's possible that these xk's are the same, but that's irrelevant in terms of this notation. But this is what we refer to as the jth sample moment. Jth sample moment of x, coming from the sample s, which range from x1 to xm. Right? So let's now formally give the definition that we're going to be working with today, and I'll go through several examples of it as well. So definition. The jth sample moment which I'll abbreviate by little m j, for a random variable x serves as an approximation for or of the jth population moment of x, which I'll abbreviate by mu j, and we'll define mu j to be equal to the expected value of xj. Here, this mu j could either be discrete or continuous. Either one is going to be perfectly okay. Where mj, the jth sample moment, will be defined to be 1 over m times the sum from k is equal to 1 to n of xk to the power of j, and mu j will be equal to the sum across all values of x to the power of j times px of x, or the integral of little x of xj times fxx dx, where the first one is for x discrete and the second x continuous. And obviously, none of this makes any sense if they don't exist. So where mu j exists and moreover is finite. Most of the time, if we grab a sample from a population, then that associated population distribution usually has some parameters associated to it, but there are a couple notable exceptions. One of the basic distributions that we usually study in the realm of statistics is the standard normal distribution, which is just a normal distribution with parameters mu and sigma, but mu and sigma having particular values 0 and 1 respectively. Once you know those particular parameters, then you can specify the distribution to be 1 over the square root of 2 pi times e to the minus 1/2 x squared. And here, keep in mind the support of this density is the set of real numbers. So one could say that this distribution has no parameters in it, or you could say that this indeed does have parameters, mu and sigma, that take some particular values. Another basic distribution that you might already know, especially in the continuous realm, would be the exponential distribution with one parameter, lambda. If you know lambda, then you know its probability density function, lambda e to the minus lambda x. And keep in mind the support is going to be x greater than or equal to 0. And in this particular case, notice that we have one parameter that guides the shape of this particular distribution. What's some other distributions that we might know? Let's go discrete. So for example, suppose that x is a binomial NP random variable. Once you know n and p, then you should be able to specify the probability mass function for random variable x, and we can write that as pxx is equal to n choose x times 1 minus p to the n minus x times p to the power of x. And remember that the support of a binomial random variable is 0, 1, 2, all the way down to m. Now keep in mind and notice that one of the parameters for this distribution lies on the support of the probability mass and or density function for the random variable under investigation. For another type of estimator that we'll discuss later, this is going to be a problem for it, but it's not going to be really a problem for the distribution or this method of moments that we're planning to present in just a moment. All right. So a question that we're going to answer is how can we estimate the parameters, let's call them theta, for px or fx in the case of continuous. All right, so let's state a nice little theorem to sort of guide us. So if x has a PMF or PDF that has parameters, let's call them theta, and keep in mind theta in this case could be a vector of theta, say theta 1, theta 2 down to theta m, then the moments of x will be functions functions of theta. That is the expected value of x, the second moment of x, the third moment of x. All of them can be represented in terms of these parameters theta that dictate the shape of the PMF and PDF. And this is just a consequence of moment generating functions if you know about them, or characteristics in the possible case that the MGF doesn't exist. So the strategy that we're going to use with this is the following, and this is going to be called MME method, or the method of moments estimation method. So this is method of moments. E stands for estimation, and the things that we get out of the method of moments estimation method are going to be method of moment estimators, or MMEs. So the strategy that MMEs use pretty much follows the following recipe. So what we're going to do is we're going to estimate mu j with mj, the sample jth moment, and then from these we're going to estimate our thetas with our mj's. Right? And it's possible that we might need more than one of these mj's, or it's possible that we only need one of them. So let's go through a couple examples to sort of see how this unfolds, and also look at how we would actually get a numerical value if we had a sample from said population. So let's consider a random variable x that is said to be, or conjectured to be, associated to a binomial NP distribution. The very first thing that you have to know in order to do MME estimation is know the theoretical representation for the nth moments. If you don't know what they are, you can always generate the MGF for this random variable x. Take the jth derivative, evaluate it at 0, and that will give you the expression for the jth moment of that random variable, which I have in other videos in case you're interested in. But x is a very famous random variable, and you probably already know the answers. But the expected value is equal to n times b, and you might also know the formula for the variance of x. That's going to be equal to np times 1 minus p. Now, the method of moments doesn't look at the variance, at least in its original sense, because they look at what we refer to as raw moments, not centralized moments, because remember that the variance can also be represented as the expected value of x minus the mean squared, which is technically the second centralized moment of x. But the method of moments looks at, for example, ex squared instead of the variance, which, keep in mind, is the variance, or np 1 minus p, plus the mean squared, right? So because, keep in mind, the variance is the second moment minus mean squared, so the second moment can be represented as the variance plus the mean squared. So once we know the formulas for the theoretical first and second moment, for which we can write as mu1 is equal to np, so that's the first thing we're going to estimate. And we also have that mu2 is equal to np 1 minus p plus n squared p squared. That's the second thing we're going to estimate. Well, what are we going to estimate them with? Well, we're going to estimate mu1 with m1, and we're going to estimate mu2 with m2. All right? So once we estimate them, I'm going to have the following representation. So that means n hat p hat, the estimators for n and p, will be equal to m1, and then we're going to have n hat p hat times 1 minus p hat plus n hat squared p hat squared, and this will be equal to m2. So we know what m1 is, we know what m2 is given a sample, and we want to solve the systems of equations for n hat and p hat. So what we have here is a system of two nonlinear equations, but generally speaking they could be linear, with two unknowns, in particular n hat and p hat. And what is this n hat and p hat? These are the MME estimators of n and p, which we're aiming for. All right, so let's see if we can solve this systems of equations, and this is where the algebra comes into the picture. Notice that we've already have n and p isolated in terms of m1, So I can just subset into the second equation and see what comes out of it. So we're going to have m1 times 1 minus p hat plus m1, the quantity squared, is equal to m2. And that gives us an equation that contains only p inside of it. So I can write this as 1 minus p hat is equal to m2 minus m1 squared all over m1. And from this, I can say that p hat will be equal to m1 over m1. That's our 1. And then minus this m2 minus m1 squared all over m1. And then I can get a common denominator and rearrange. And I can write this as p hat, MME, or MME estimator for p, will be equal to m1 squared plus m1 minus m2 all over m1. So that's our MME estimator for p. Now once I have p, now I can use the first equation in order to solve for n by dividing both sides by that. So that's going to give us what? So we have n hat, p hat will be equal to m1, which means that n hat will be equal to m1 over p hat. Right, so we need to reciprocate this particular expression and then divide it by m1. And that's going to give us m1, the quantity squared, all over m1 squared plus m1 minus m2. So this is going to be equal to n hat MME. And that gives the MME estimate for the number of trials that was in this particular sequence. Right? So that's how you can derive the theoretical MME estimates for a particular distribution that has some particular parameters associated to it. Now let's look at a practical example of where you might want to use these. So let's suppose that a set of individuals are allowed to play a game a fixed amount of times, the same number of trials for all of them, and let's assume that each trial is independent of one another by experimental design, and let's assume that the probability of each of those trials for each of those individuals is fixed for all of them, again by experimental design. Let's suppose that the individuals report the number of successes in their trials to be as follows: 5, 3, 4, 7, 2, 5, 4, 3, 5, 2, 3. So this is going to give us our sequence. So how many do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 trials. So we have 11 people in our particular sample. And what do we want? So if we assume that these trials are independent of each other and the number of trials is going to be fixed, let's call that, for example, n, and let's assume that this probability of success is going to be little p, we need to figure out what is n and what is p. Notice that all of these values in this particular sample are floating somewhere around 2 to 7. So it's not really that intuitive that n is going to be large. So the values in our sample are not large. So we have quite a few cases to consider here. N is around, let's say, 10. That would be at least an intuitive guess. Or B, n is large, but the probability is significantly less than 50%. Or, and keep in mind, this is a sample, so it has all the issues that samples could have. So C, the observations are not well representative. Right, but the non-well representative thing, C, we can't really consider here. So the only things we really can look at here, at least given this information, is how to estimate n and how to estimate p. And the method of moments estimation gives us tools to do this. All right, so let's assume that we want to use MMEs to generate estimates for n and p. So again, m1 is equal to 1 over n times the sum from k is equal to 1 to n of xk, which, keep in mind, is going to be equal to x bar. And m2 is going to be equal to 1 over m times the sum from k is equal to 1 to n of xk, the quantity squared, aka the sample second moment. So using our particular sample values, you should be able to find that m1 will be approximately equal to 3.9091, and M2 will be approximately equal to 17.3636. Keep in mind, for any given sample of finite values, you can always calculate the values of M1, M2, M3, M4, and so on. Right? So what are the formulas for p hat MME and n hat MME? Well, we just derived them. So for binomial, this is going to be m1 squared plus m1 minus m2 all over m1. And this is going to be equal to m1 squared all over m1 squared plus m1 minus m2. And keep in mind, these formulas are specifically for the binomial distribution. So if you have another conjecture of a distribution that these are going to be associated to, then you have to derive their own MME estimate representations for those particular parameters. So using our values of m1 and m2 and then substituting into our relations, you can find that the MME estimate for p hat given this particular sample will be approximately equal to 0.4672, and this is going to be approximately equal to 8.3665. So, based upon MME estimation theory, we have evidence to believe that the probability of success for each of those trials was somewhere around 47%, and the number of trials that each of these individuals were allowed to play this game was somewhere between 8 and 9, leaning more towards 8. Right? Now, a very interesting question that I leave for you is the expected value of p hat MME equal to p is the expected value of n hat MME equal to m. I leave this exercise for you. I'm just going to give you a little spoiler alert. They're not necessarily exactly equal to these values, but they are roughly close, but there is some bias associated to it. But the distributions of p hat MME and n hat MME are not exactly the easiest to construct, but you can always approximate them. That's not a big issue, right? But keep in mind, these are estimators, so you can consider the bias or lack of unbiasedness for these estimators. And this also goes for other adjectives that we'll discuss later, such as consistency and efficiency, and so on. So let's look at another example for how we can construct MME estimates for parameters for continuous distributions, like we did for the binomial, which is a discrete. Now let's consider the case where x is a normal random variable. Again, if it's normal, there's two parameters that we're going to be seeking to estimate, mu and sigma squared. So you may remember that the expected value of x will be equal to mu, and the variance for x will be equal to sigma squared. Therefore, the second moment of x will be equal to mu squared plus sigma squared. So mu squared plus sigma squared. Right, so this is going to give us expressions for our first theoretical moment, mu1, and our second theoretical moment, mu2. So therefore, approaching this in the same exact way as we did for the binomial, we're going to have that mu hat will be equal to m1, and mu hat squared plus sigma hat squared will be equal to m2. And this is going to give us a system of two equations, two unknowns. From the first equation, it's actually already solved for us. So therefore, we can say that mu hat, MME, will be equal to m1, also known as x bar in disguise. And then sigma hat squared, so sigma hat squared, MME, don't forget your square on that, that's going to be equal to m2 minus m1 squared, also known as 1 over n times the sum of our xk squareds minus x bar. So those are our estimates for mu and sigma squared via method of moments estimation theory. Now let us see if we can assess the unbiasedness or lack thereof for these particular estimators. So what is the expected value of mu hat MME for normal? So in this case, that's going to be equal to the expected value of x bar. And you may have already proven this on your own, but the expected value of x bar will be equal to the expected value of x, and that's going to be equal to mu. All right, so therefore this is an unbiased estimator for our population mean mu, right? So that's actually a very nice property. Not the nicest, but it's definitely a nice property that we can have for MME estimates. So let's see if the sigma squared MME is just as nice, just like its counterpart mu hat is. So hopefully the expected value of sigma hat squared will be equal to sigma squared. So let's check that out. So this is going to be equal to the expected value of 1 over n times the sum from k is equal to 1 to n of xk squared minus x bar squared. So what I want to do is I want to distribute this expectation over this sum, in particular to this object and that object, and also inside of the sum as well. And that's going to give us 1 over n times the sum from k is equal to 1 to m of the expected value of xk squared, or the second moment of xk, minus the expected value of x bar squared. And again, make sure you have your squares in the correct position. So we already know the relationship between expected value of xk squared and the expected value of x bar because they're related to the mean and variance of x. In particular, this first expression is going to be the sum from k is equal to 1 to n of mu squared plus sigma squared. And then this last expression, keep in mind the second expression doesn't have a sum on it, is going to be equal to mu squared plus sigma squared divided by m, right? And that's by properties of the expected value of x bar and also the variance of x bar, which is the variance of x divided by m. Right? So once we have this particular expression, now we can start to distribute and simplify and all that other thing. Also, let's make sure that our bracket is not including anything for which the bracket is not supposed to be associated to. So notice that this expression is independent of k, so that's just mu squared plus sigma squared added to itself n times. So that's going to be equal to 1 over n multiplied by n mu squared plus sigma squared. And then we have minus mu squared minus sigma squared all divided by m. Those n's are going to cancel from the front, which is actually pretty nice. And then we're going to have mu squared plus sigma squared minus mu squared minus sigma squared all over m. Those mu squareds are going to cancel out each other, and then we can factor out a sigma squared. So 1 minus 1 over n times sigma squared. So this is the expected value of sigma squared MME. Right? So obviously this is not equal to sigma squared, which means it is a biased estimate for sigma squared. But it does have one slight sub-advantage to it, because if we take the limit as n goes to infinity of the expected value of sigma hat squared MME, notice that 1 minus 1 over m, because 1 over n goes to 0, and then we're going to have 1 minus 0, which is 1, this is going to be equal to sigma squared, right? So that means it is asymptotically unbiased. So asymptotically unbiased, right? Asymptotically unbiased, which is better than nothing, right? So we have here estimates for mu and sigma squared for normal distribution. And if you have a sample, you can plug numbers into these particular expressions if you really want to, right? And we find that the MME estimate for mu is unbiased. And we find that the MME estimate for sigma squared is biased, but at least it is asymptotically unbiased. Okay? So that's how you can actually use method of moments estimators to generate approximations for any parameter of any distribution that you want, as long as they exist and are finite, and as long as you can do the algebra that is required to solve the associated systems of equations. I hope you enjoyed this video, and I'll see you in the next one. Take care.